I received a new meter. It's this Fluke 17B Plus. It came with this set of probes. It measures temperature, so it came with a standard Fluke thermocouple. I'd rather have a standard adapter so I can use a normal thermocouple with it, but this is what came with it. These appear to be the same leads that were supplied with the Fluke 101. So why this meter? Somebody had asked about testing the 15B Plus. It's a newer meter, and I started looking at it. It looked pretty good, but then I noticed this 17B Plus. It's got temperature input. I thought, yeah, really for me, if I was going to buy a Fluke meter, I'd probably pick something like this over the 15B, just for that temperature input. So I'm not going to do a full review of this meter, but I thought rather than just hook it up to the transient generator and see where it fails at, I thought I'd take some time to compare this against some of the other meters that I've looked at. So if we look here, this is one of the first meters I tested. This meter sold under the Centec brand. It's a part number P98674. This is a rebranded Maztec MS8268. This meter's 2,000 counts. What I like about it is that it has a photometer. It can measure lux. It also has a sound pressure meter in it. It also has an internal temperature sensor. It's kind of cool how the connectors here will light up as you go through the modes. Makes it very easy to understand, I guess, where to plug in the leads. So overall, I've been pretty happy with this meter, but I can tell you firsthand, this meter, it's not very robust. You have to kind of treat it with kit gloves. So again, this is roughly a $50 meter from Harbor Freight. Next up would be this AM510. This meter also does not have RMS, just like the Maztec here. And again, it costs like $50. Also in the $50 range was this Fluke 101. So this thing currently sells for like $48. The thing I don't like about this is it's missing a lot of features. It doesn't have a backlight, for example. It can't measure any kind of current. And it's very slow on the continuity test. However, this thing, again, very robust. I hit this thing with some pretty harsh transients and it survived just fine. I've yet to take this meter apart. Next on the list would be this Amprobe AM530. This meter actually does have RMS. This cost about $80. And again, this was supplied by 5KY. So both of these are a 4,000 count meter. The big advantage of the 530 over the 510, besides it being RMS, is that it has a temperature input and it also has a bar graph display. Next up would be the Fluke 107. This meter currently sells for $108. Again, very robust meter. This is a 6,000 count. One of the things I don't like about the meter is it only does AC millivolts, not DC. It also has no lower ranges for current. But for $107, probably a fairly nice meter. It's definitely very robust. So next up is the 17B Plus. This meter currently sells for $156. It's also a 4,000 count, just like the two Amprobes here. It does have a temperature sensor. It can do DC milliamps and microamps. And it also does DC millivolts, which the 107 cannot. It has the feel of a very well built meter. I'm kind of surprised that it doesn't support RMS, but again, it is kind of a lower end meter. So if you're needing RMS, I would say this Amprobe may be a better meter for you. And of course, then we have my Brightman BM869. This is the meter that I normally use now. I'm very happy with it. But again, this has a price of about $230 if you buy it without the serial communications. So I've verified this meter for accuracy, and it does appear to meet the manufacturer's specs. I thought what we'd do is compare it against a couple other meters. If we look at the AM530, you can see here off to the right there's amps, milliamps, and microamps. When we look over at the voltage selection, we could see it's an AC/DC volts, and the mode is set by the select button here. But you don't see anything for millivolt range. Compare that with the Fluke 17B Plus. We can see here it has a millivolt range. And of course, then we have the Maztec. And again, you see the same thing. There's an amps, milliamps, and microamps. And again, just a single voltage selection. You select the mode by pressing the select button here, but not a specific mode for millivolts or microvolts. These 3 meters are tied in parallel and they're attached to my Fluke reference. You can see the amp probe comes up with AC volts, so it has to be selected to DC. Putting out a 1 millivolt signal right now. We can see here it's reading 0.9 on the Maztec, 0.9 on the 17B Plus, and 1.0 on the amp probe 530. And now I'm going to select 1.019 volts. You can see the amp probe's off by a little bit now. The Maztec is fairly close. We have to switch the range on the Fluke. This is with 1 volt applied. You can see the Maztec is reading dead on. The amp probe again is a little high, and the Fluke is reading a little bit low. And this is with 10 volts applied. And we can see the amp probe's off by about 50 millivolts. Fluke is also off by about 50 millivolts. So just because the 2 meters here don't have a millivolt range, they actually do a fairly good job reading down into the millivolts. As a matter of fact, in my opinion, it's kind of nicer not having the extra switch position if the meters will just auto range. All 3 meters are still set to their DC modes, and all 3 are now connected to my ARB. The ARB's output voltage is 0 to 5 volts, and it's sweeping that in roughly 10 seconds right now. This will give you an idea of how fast the meters are responding. As we can see, they're all very similar. As far as robustness, this AM530 you would think probably would be on par with the AM510. I guess I don't know that for sure. While the AM510 had made it all the way to the finals with the Fluke 101, this AM530 failed pretty early on in the pack. And the problem with that is that I can't really draw a conclusion between the 2 sets of tests. I had actually changed the transient generator, so moving forward I can compare the meters, but going back and trying to compare like where the first set of meters were tested at and where they would fail against this set, it's a little difficult. So I'm assuming that this Fluke 17B will be much better than what this amp probe AM530 is, but that's really what we're here to do, is to repeat that test. Next, I'd like to show you the difference between these 2 meters, because I know the Maztec will fail at a lower energy than the amp probe AM530. What I thought I would do is just use this one as a comparison against this Fluke. So I thought what we'd do is take these both apart and kind of compare how they're constructed. I've damaged this meter. I had replaced Q9. It's one of the nice things with the amp probe. See, it's got the metal insert and the battery just pops out. I'm not a big fan of the pink sponge here that holds the battery in place, but we just rotate the latch and the batteries fall out. So there's nothing really that holds these in place, and just laying loose in there, at least with this, you know, not like bouncing around, but again, not a big deal. Probably not changing the batteries all that often. So to get into the amp probe, there's just a couple of screws here. See both ceramic fuses. 1000 volt part here. I haven't changed any of these out. This is just what the meter had in it. To take the Fluke apart, we first have to remove the outside rubber sleeve. You can see here, instead of 2 screws, there's actually 6. This decal here is to cover up for the calibration. And I'm not sure which is worse, having mechanical contacts like this, or just having them soldered into the board like the amp probe. So on the amp probe, this is the 11 amp fuse, and this is the 0.5 amp fuse. See the high voltage resistor. Here's the PTC versus the PTC on the Fluke. Got the 3 MOVs up here. Connectors seem a little bit nicer construction. Now, one of the things I'd noticed with this Fluke, maybe a little difficult to see, but yeah, see this slight blemish right there? That's actually grease that's coming out from the two vias. The same thing right there, that's grease. And it's probably a little difficult to tell, but there's quite a bit of grease coming out of the rotary switch. If we had looked here on the back side of the cover here, that's all grease off of the rotary switch. So this thing is actually loaded up with grease. I don't know why they put so much in excess on it. Yeah, that gives you an idea kind of how the two are constructed. A lot of these meters I can't repair. If it blows out the main control IC, for example, there's nothing I can do. Sometimes I get lucky and it just fails, like maybe a diode or something, or a resistor will blow. Some of those meters I've been able to repair, but the ones that you just saw me look at, those are pretty much all the ones that have been damaged and repaired. Nothing else really exists anymore. It's one of the things with the amp probe. You can see they're still using potentiometers to do the tweaking. The Fluke, on the other hand, you can see here it's got a communications port to do the cal, and that's what that decal is covering up in the back. Overall, the quality is pretty good on this. You can tell the plastic on this is really stiff. It's got a good feel to it, a lot of heft. I like the meter overall. I'm not a big fan of the price for it. I think really I'd probably pick this amp probe. Very similar specs, and this is a $80 meter, or about half of the price. And it does RMS, which the Fluke does not. And as you can see, the voltage specs for the two are very similar on the DC volts. So again, not having the millivolt range here, not of an issue. This thing just auto scales down. So yeah, similar. So I thought, for fun, let's just put the batteries back in these. So the first thing you got to do is figure out the polarity. So on the amp probe, you look down inside the hole here, and you can see the battery polarity, plus being on the right. So it pretty easily just slides into the cover here, and it just pushes down in, set your screw, and you're good to go. And fairly nice. It's got the steel insert, so not too bad. Fluke, on the other hand, we can see it's marked here. So you kind of lay these in. So the first thing you got to do is open this thing up. You can see it takes a little bit to get that going. And slide it in. And then you can set your latch. And you can close it up. Of course, you still got the rubber boot. So some time ago I looked at the continuity feature on the meters I had left. I was trying to find a better way to characterize it than just touching the leads together. And so I came up with a set of test criteria, and I think what I'm going to do is run the Fluke through that. I've already have a matrix started with a few meters in there that I'd collected the data from. This Unity, this is actually the only Unity meter that I have left. Currently I've damaged 3 different ones beyond repair. This is a UT90A. I've damaged this meter twice now. Its claim to fame is probably that it's the only meter in the world that's ever played Van Halen's Eruption. If you watch 5KY's original review of the 530, one of the things he was complaining about was the continuity test on this. And you can see it is slow. It's just terrible. And I was amazed because I had ran the 510 and it's very fast. And it's not the leads. So this meter, it's not good at all for continuity test, at least not the way I would use it. I haven't even looked at the Fluke, to tell you the truth. This will be the first time I try it. So I think what I'm going to do, I haven't measured the amp probe, so I'm going to measure both of these. Okay, so the first thing we want to do is measure the open circuit voltage. This is connected to a benchtop meter. It's a 34401 that's in current cal. So the Fluke is reading 0.5314 and the amp probe is reading 0.4220. Next we want to measure the short circuit current. Okay, the next thing we're going to do is use this decade box to determine the threshold resistance that the meter actually detects a short. Then we want to see at what point it opens. Then we'll do the same thing for the amp probe. The next thing I'm going to be doing is shorting these inputs at a 50% duty cycle, and I want to know at what frequency the meter starts to miss pulses. You can hear there where it's missing, and here where it's not. You can see the Fluke's missing at that frequency already. Next thing we're going to do is short this out at a 2 Hertz rate, and we're going to control the duty cycle, and we're going to measure the minimum pulse width that it takes for this meter to detect a short. And we'll do the same thing with the Fluke. Looks like about right here. Maybe one wider. So this is the data I've collected so far. Down here we can see the 17B plus. So with a 50% duty cycle wave going into it, it was good to about 1.7 Hertz. Compare that with 5.6 for the amp probe, 8 Hertz for the other amp probe, the 510. Again, my 510 was quite a bit faster than 5KY's 530. But then you look at the Bryman, it's over 100 Hertz. And the Unity and the old Syntec are both above 10 kilohertz. This is how we ended up trying to play music out of that Unity. The minimum pulse width of the 2 Hertz signal coming in, you can see the Fluke is 20 milliseconds compared to the 530 at 150. So while the pulse width going into the Fluke can be quite a bit shorter than the amp probe, the top end frequency is very low. So for my own application, I'd actually be better off with this amp probe. I'd rather have the higher frequency. Actually, like this 510 here at 8 Hertz, that's almost perfect for what I would be using it for. And that'll also detect a 20 millisecond pulse width. You can see the Fluke is at 84 ohms where it detects the short, versus the amp probe 530 at 40 ohms, and it releases at 90 ohms, so giving you roughly a 6 ohm hysteresis compared to 43 ohms or a 3 ohm hysteresis on the amp probe 530. You can see the open circuit voltage for the Fluke, it's in the ballpark. It's 0.531 versus 0.422 for the amp probe. Current wise, it's 177 milliamps for the Fluke, 158 milliamps for the amp probe. Hey, it's a new day. Thought I'd run the remaining tests on this Fluke 17B. I think before we do that, Let me just show you here. I've modified my box here a little bit. This is what I've been using to check my meters. You can see I've added 3 silicon diodes in series here. The only thing I've done was put a K-type thermocouple in the box. And I've also added a 5 volt reference. This is a Apex VRE 305 IC. The box isn't temperature controlled, so this voltage will drift around a little bit. There's a push button on the side to enable power to the reference. I've also added a 100 and 1000 meg resistor. I've also added a 1 mic and a 10 mic ceramic capacitor. Other than that, really no changes to the box. We're going to start the test with the piezo grill igniter. Again, we'll do positive and negative transients, 5 each in each mode of the meter, and let's just see if it'll survive. Okay, let's do a basic checkout. And first thing we'll do, look at the AC volt. About right. DC volt. Looks good. So 1 ohm resistor. Here's a 50. 100. 1K. 10K. 100K. 1 meg. 10 meg. I think this meter's only rated for 40 meg. We can try it with 100 meg. I don't think it'll pick it up. Yeah. Continuity test works. It's 1 diode. 2. Yeah, looks pretty good. So here's a 1 nanofarad. Pretty small for this meter. This is a 0.1. Pretty good. And a 1 microfarad. Yep, looks pretty good. And a 10 mic. Again, looks pretty good. Have a look at the thermocouple. Yep, looks pretty good. So yeah, let me go through and I'll verify the full functionality of this meter, and if it looks good, we'll go on to the next test. Next step, you can see I've got the high voltage supply out, and we'll go ahead and increase this and make sure that it'll survive at least 1000 volts DC. And that's the limit of my supply, so very close to 1000 volts. Yeah, so that looks good. So for this next set of tests, what we're going to do is use the new generator to output a rectified 220 volt AC signal, and we'll supply that into the Fluke and run the Fluke through all of its modes. And you can see the light comes on. It's definitely live. Okay, that's it. Go ahead and functional test it. Yes, I'm not surprised. Everything looks good. No problems whatsoever. So next step, we'll start injecting transients. So again, this will be 5 transients, both positive and negative, in each mode of the meter. And then we'll functional test it. So this will be 1 kV. Okay, that's it. You can see we're at 500 volts per division and 100 microseconds per division. So about 1000 volts again. Full width half height of roughly 100 microseconds. Again, these waveforms are all controlled by this box. That's the reason I built this, is so I could go back and reproduce these tests. So yeah, let me go ahead and check the Fluke out, and we'll make sure that it's still okay. Alright, next up, this will be 1.5 kV. This is kind of a significant milestone. The 87V that I tested actually failed at this level, and so did this Amprobe AM530. Okay, so hopefully this will pass this test. Let's give her a try. Okay, I'll go ahead and functional test it. Let's have a look. Yeah, so it looks good. So yeah, this is actually a little more robust than the 87V. And it's also more robust than this Amprobe AM530. It's impressive. Also, what had failed at that point was the TP40, I think. Yeah, the Tech Power TP40 had failed at that level. So at this next level, the Klein MM2000 failed. Just to give you a reference. So let's see how this 17B does. So again, this will be 2 kV. Alright, that's it. We'll have a look. Yeah, so it passes all of its functional tests. No problems at all. So again, more robust than the Klein Tools MM2000. We didn't have another meter fail for a while. So to give you an idea, 5KY's Radio Shack 220087 was still in play. The Fluke 107, obviously. The Hold Peak HP 760H, and of course my Bryman was still in play, but only those 4 meters had survived to this point. So next up is 2.5 kV. Okay, that's it. We'll go ahead and check it. Okay, it passes functional. So again, this will be 3 kV. Alright, let's have a look, see if it passes functional. Okay, it passes functional. It's looking good so far. From here on out I was incrementing by 1,000 volts, so this next test is going to be at 4,000 volts. Here we go. Okay, that was 4,000 volts. The meter survived just fine. We'll set the generator for 5,000 volts next. Okay, I finished verifying functionality. The 17B Plus is just fine. I thought I'd mention the one meter that did fail at 5,000 volts was the Hold Peak HP760H. From the second round of testing, the only meters that had survived to this point was the Radio Shack, the Fluke 107, and of course the Bryman. So this last set of tests is going to be at 5.9 kV. And I think what we're going to do is measure this again with a scope and just verify this, because it is the high end of the generator. So we'll go ahead and set that up first. So I plugged the generator into the little distribution block here, and I'm going to be using these other set of cables. This is just an easier way for me to monitor with a high voltage probe. So if something does break down, if I'm monitoring with the scope, I can usually detect that pretty quick. So again, this is roughly 5.9 kV and about 100 microsecond full width to half height. Should be good to go. Near the LaCroix recaling, because it just got a trigger, because that's what it does. Of course, it's got nothing to do now, so it's not doing any autocal. It looks fine so far on the scope. Hadn't noticed that the camera shut off here. I don't know if the batteries are failing or not. Anyway, we're almost done with the test. Yeah, it's too bad. I didn't even notice it. Well, this is the last transient of the set. Again, I'm not sure how much video we lost here, but rest assured we actually did run all the transients, so there you go. We'll go ahead and test it out. Okay, I've just completed all the functional tests. Meter's still fine. This is one of 4 meters that have passed this test. So, fairly impressive. We'll have to decide what to do with it next. The original transient generator had been rebuilt to find the limitations of 5kW's Fluke 107 that he had sent. And so that's currently set for about a 20,000 volt spike. So I would need to maybe set that back to what the original Fluke 101 had passed to or something. So just to summarize, this spreadsheet shows all the test results. The highlights in yellow are where each individual meter failed. NT here, that means no test. And you can see in that case, like the 87V, I never ran those tests until the very end. And that's where it failed at. That's what I was saying, we never really knew where that meter had actually failed. You also see the same thing right here, and that is the 139C. Again, that meter came in late, so we weren't able to run it along with the rest of the meters. These are the ones that 5kY had sent me. Down here we can see where we actually ran the Fluke 87. And we didn't run the static test or the high voltage testing. And it had passed at 1 kV and failed at 2. As you can see, quite a few meters fail in that range. So this last column here, this is our Fluke 17B. It's passed everything up to this point. Basically right there with the Bryman so far, Fluke 107, and 5kY's Radio Shack meter. So yeah, give me some time here. We'll sort out what we're going to do with the generator. I may set up something where I can actually do more discrete tests up in this higher voltage area.